I'm telling you, it's one of the
pillars.
no. When you live abroad, it's like, oh, the IDF, smart and swift and kill our enemies. And when you enter the IDF, you're like, oh my God,
How are we alive?
yes, that's it. This moment for us, how do we have to do something, but you get used to it. Okay, so enough talking with municipalities. It can be very, very draining. Why doesn't it work? Okay, so Info 2 lecture C is so much fun. Um, I choose different color and do it for the spoiler, as we already knew from, I don't know, lecture 3 or something like that. Integral from A to B of F is big F at B minus big F at A. I'm planning on getting to this theorem today. Of course, there's some conditions, not that simple. But on the way, we have to meet some new notions about definite integral. We should start with a little reminder to some of the properties we showed last at our last lesson. So we saw some of the properties of the definite integral, including, I was trying to write down only the important ones. First of all, linearity. Right? The integral of alpha f plus g is alpha the integral of f plus the integral of g. It's a monotone, meaning that if f is smaller than g, then the integrals behave similar way. In our last lesson, we explained it. What's the logic behind every property I mentioned now? What else? What else? The triangular inequality. What? Yeah, because it's the same line as the English text. If I put it in a different um, environment, formula environment, so it gets better. Are you going to print the PDF after the lesson? So
No.
uh, another page doesn't really matter. Yeah. As far as I know, today, as of today, they are planting the trees specifically, specific trees, some species of trees in order to manufacture all the paper. So ironically, using paper helps the environment because they plant a lot more trees. Something like that. It's like that legalizing how do you poaching when you hunt wild animals. Poachers, yeah, poaching. Some of the African states, like Zambia or whatever, I don't really know. Some of them in some of the areas in their national parks, they have some kind of legalized poaching, and you have like a financial interest to have more elephants and more rhinos and more whatever. So ironically, having the poaching legalized helped the animals' population grow in some twisted way. So as far as I understand, right now it's something that similar with the trees. the they're spec I'm the Lorax, I speak to the trees. So there's some kind of specific species of trees that uh, manufacture the paper from, and just make them plant more trees like them. What else? What else? Um, I don't know how to say this. It's called the additivity of the domain, we called it. The integral of from A to B is like the integral from A to C plus the integral from C to B. What else do we need to know? We call it the intermediate value theorem, but in the language of the integrals. And there is a point C in A to B, which satisfies integral from A to B of f is fc multiplied by the difference between b and a. Of course, when f is continuous, here, only when, it sounds like it's if and only if it's not if and only if, when f is continuous. I think that's all. Second thing we need before we start is it's a definition after all, but it is very intuitive, so one can think of it as some statement or something, but it's a definition. And now we define two things. First of all, the integral from a point to itself, no matter what a function is zero. It is very logical because hey, what's the area beneath one single point? Zero, don't have any area. It's maybe a length of an area. It doesn't exist, but by definition, the notation of integral applies only to a function above some segment. So we actually cannot talk about integral above 1 point. So we define it to be zero. The definition and our logic gets together, but it's the definition after all. Yeah.
When you say f is continuous, is that for everything just above?
No, just for five. Just for five. Yeah. Make weird noises. Why is that? Just for five. And B, we define the integral from B to A, where B is greater than A, to be the negative of the integral from A to B. Again, it makes some sense. I think about the integral as fb minus fa, I mean big FB minus big FA. So from B to A, it will be FA minus FB, this minus. But still, it's definition. The notion of integral is defined for a segment from A to B, from the small to the greater one. And if we change the order of the limits of the integral, we put the minus sign behind it. So with these properties and with this definition, we can start our journey. Our main goal is the theorem about the big F. It is called, not a spoiler, it's called the fundamental theorem of the calculus. Not every theorem is the fundamental, right, of our main subject. So it is important. But as I mentioned, we have some way to walk before. Any questions about what we just said? Okay. So, let's write down as a title the area function. let f be a function, number הכי טובים, find at, I don't know, segment between A and B, as we usually do. The integrable. We need an integrable function. If it's not integrable, it is not well defined. So we denote with, let's write down as S, Sx. You can write Ax or area, the area function. The S is defined by S of x is the integral from a to x. We use x as one of the limits of the integral, so we cannot use the same letter inside the integral. So I choose to use the letter t. Intuitively, S counts how many area we've already obtained between the function and the x-axis from the point A till the point X. Let's write it down intuitively. That's how you write it. If not, so feel free to correct my typos. Intuitively, S is counting the area obtained between f the axis from the beginning of the segment and 2x. Let's have an example we can, touch, we can feel with our hands, but we can write it in a different color. It's not very important, the example itself, because all this area function stuff is our main goal to prove the theorem about the big F. It's just a helpful tool, nothing more. But let's have an example. For example, we'll look at fx is x in or add whatever 0 and 1. We can say that manually by hand calculate the area. Let's have a drawing. No, I'm from the beige background. Axis. That's the y-axis. And our function for different color. Let's see what pink. This is a function. We start at the point 0, and we are finishing at the point x. So it is 0, and here it's x. What's the area we've already obtained between the function and the axis? It's triangle, and we can calculate triangle's area with x, and divided by 2. Which is x squared above 2. Now, as usual, I just paste it back to the PNG before we continue. limit, so this will be a font blow up. 6.5. Good. So here we can manually calculate the area for a bit more complicated function we want to work, but we can write down, let's keep it with the blue. So we have that Sx, which is the integral of f from fs to f, 0 to x, is actually x squared above 2, and yet again, fx is x. I can't answer it right now. fx is x, so ft is t. I'm sorry, it's 6 by way. זה חשוב אשתי, אני באמצע שיעור. Sorry for that. 2907. כן. ביי. So the area function of x is x squared above 2. Coincidence. That's the antiderivative, right? Ma. Okay. Bye. So the area function gives us, in this, of course, specific case, again, I put it in blue because it's just an example, not very important, but it gives us an antiderivative. And we'll take a few more steps in order to get our main theorem of big F. And our first step, as we mentioned, is the area function, which gives us actually the antiderivative. The problem is how to calculate it when the function is more complicated. So that's our area function. And I want to state some statements about it so we can move on. Questions about how we define it? Direct question? Okay. So our first theorem or proposition, if you like, will be proposition S is continuous. And I want to prove it. Okay. Continuity is property, call it per point. In every point C of our segment A to B, we are claiming that F is continuous. So we actually have to start from let C or whatever be some point at A to B. We want to show that S is continuous. Continuous at C, meaning that Sx goes to Sc, not to Sx, of course, when X goes to C. So we know what Sx and Sc is, and we can use the definition in order to prove our statement. So equivalently, that's how you write it. We need to show that the difference between Sx and Sc tends to 0, and it is enough. It's enough. It is enough to show that the absolute value of Sx and S difference between Sx and Sc tends to 0. Mathematicians love to go to the absolute value when they need to prove that something tends to 0 from a simple reason. When we use the sandwich theorem, the absolute value gives us one of the slices of the bread free, for free. And absolute value is always greater than 0. We just have to find something greater that tends to 0 as well. And from sandwich, we'll have our difference go to 0. And what is convenient that when it comes to 0, the absolute value and the difference itself tends to 0 equivalently. Now, from different number, it doesn't work. I mean, the absolute value tends to, I don't know, 12. The difference can jump between 12 and minus 12 and something like that without any convergence. But when it tends to 0, the expression itself without the absolute value will tend to 0 as well. So, enough talking. That's math. The difference between Sx and Sc is S is defined with the integral from a to x. And Sc is the integral from a to c. Now, I want to use the additive property of the integral. We know that the integral from a to x is the integral from a to c and the integral from c to x. Put it down so we can from the good integral. Let's write it in top and not just int. Again, the integral from a to x is the integral from a to c plus the integral from c to x. So we can move one of integrals to the next side, and we have that the integral, the difference between the integrals ax and ac is just the integral between c and x. So what do we have? We can write down the difference of the integrals as just one integral, more convenient. Integral in between c and x. Now, what can we say about, yeah?
How can we do what you did in not this line, the last line without like using what we are proving?
We're trying to prove that S is continuous.
Uh,
This is one of the properties we mentioned in the start of the lecture we showed last week.
well, I'm trying to understand if you did that.
We call this this line.
Yeah.
We call this property, I don't know, the additive of the additivity of the integral, something like that, where the area between the function in the x-axis along a and x is actually the area from a to c and the area from c to x. Now we moved the integral of from a to c to the left side of the equation. and we got the difference between the integrals, it's actually one integral, the integral between c and x. And what we have here is the integral of the absolute value of the integral. And as we know, we can bound it with the integral of the absolute value. That's another property we mentioned. So it's not equal, it's less or equal or less the integral of the absolute value of f. Now, we don't know that f is continuous, so we cannot say it's just f at some point multiplied by the difference between x and c. Because if I could write something like, I don't know, f, we already used the letter c, so let's say fd or something, multiplied by x minus c, well, when x tends to c, this is tends to 0. Simple. But we cannot say that because we don't know that f is continuous. We only know that f is integrable. But we know that if f is integrable, it is bounded because f what?
One of the properties of integrable is that it's an antiderivative, and the other one
Yes.
is
So we know that's integrable, and so it is bounded. There is m at r such that absolute value of f is smaller ft, whatever, is smaller than m. And we get from the fact that the integral is monotone that it is smaller than the integral of n. Now, the integral of constant function, as we saw in lecture 4, is the constant multiplied by the difference of the limits. And when x tends to c, let's do it with underset for the effects. When x tends to c, it does. It tends to 0. And by sandwich, we get that the difference in the absolute value goes to 0. And so the difference itself without the absolute value tends to 0 as well, as we needed. That's a right required. Yeah. No, it's yes, f is integrable. It's like our default. When we first defined what the area function is, we stated that f is integrable. All our discussion is about integrable functions. Just a sec. My wife got me notes.
yeah, those is the complex.
Second.
No, it's something like find an integral that an antiderivative that is find a function that has an antiderivative that is not integral and the other has no bound.
If we have time allowed, I'll talk about it in this lecture as well. I mean, Nir talked about it probably in the practice or the homework, but I want to mention it here as well. The difference between after we show our big theorem about big F, etc., etc., there's still difference between antiderivative on one hand and integrable functions on the other hand. So first of all, it's one of the definition. Integral bounded is a function. Integral function is a function that is A, bounded, and B, every Riemann sum goes to the same limit with all these partitions and point choosing, etc. Omega is it's an equivalent condition. The sum of the omega goes to 0. Um, what?
It's bounded
An interval.
it doesn't go to infinity.
For example, every continuous function is bounded in some interval. No, it's not bounded all R. Yeah. Okay. So our next theorem, we'll call it theorem, not just proposition. Theorem. It's the fundamental fund. It's without E or with E? I mean, you say it without E, you pronounce it without, but there is E, right? That's how you write fundamental? That's how you write the word fundamental, or without the E?
No, fundamental.
Funda. Okay. Good word. Fundamental, a theorem of calculus. It's a very big name. It's part 1. Can I cover all the fun at one time? It says the one can state it more precisely than I stated, but the way I put it is more than enough for everything we need to know when to do and to solve. So I'll write it that way. Let f be an integrable function in area AB if f is continuous at some point. Let's write it down and let C be some point from A to B. Now, מה קורה? You want to learn in English? They are second year. They already finished with Infi. Not for long. You'll be there as well. Calling me from outside. If S continues at some at C, then S is differentiable at C, and derivative of S is F. Generally speaking, so if F is continuous, not that, just at some point, but continuous for every point in AB, then S is an antiderivative derivative of F. As our example of X and X squared above 2 showed, it is generally correct, but you see with one main condition, which is not always happens. When F is continuous, then this function S is F antiderivative, is antiderivative of F. This part 1, and after we prove it, we can write down part 2, which is our theorem of F gadol, of big F. So I want to prove it as well. And we use the definition of derivative. That will be better to write down. I could have some zoo or something. כמה הם שם? בואו נרביץ להם. כמה הם? אני לא יודע.
לא, הם בשלב סטטיסטיות לדודי מחשב, כאילו, קנה ושמים את ה...
So they're suffering enough. Okay. So only got the punishment. We use the definition of the derivative. We need to show that the limit where age goes to 0 of SC plus age minus SC above ed is FC. By definition, this nice limit is derivative of S at the point C. So we want to show that, first of all, it exists, and moreover, it equals FC. So let's write it down. It will be similar to a last proof because we have the difference here between S and we know what S is, the integral, blah, blah, blah. Let's see what we can do. Of course, we'll need to use the continuity of F somewhere along the way, but shwaya shwaya, as we say in Hebrew. The definition of S gives us, I write it down that way. I take the age and put it aside, so the integrals will be written nicely, not with some weird way as they are in the line of text. The integral from a to c plus age minus the integral from a to c. All right. So again, we have our nice property of additivity of the integral. One can write that the integral from a to c plus the integral from c to c plus age is the integral from a to c plus age. So the difference between the integral a to c plus h and a to c is just the integral from c to c plus h. We get that this difference is the integral from c to c plus h. Of f t dt. Now, we can say that f is integrable, so it is bounded, and this exists in M such that blah, 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 as in our last proof, but we want more. Not just 0, we want to show it, we want to actually have it as FC at the end. So here we use the intermediate value theorem in its integral language, and we can use it because our condition here is that f is not just integrable, it is continuous. Now, f is continuous, so we can use the intermediate value theorem. There is the segment now is from C to C plus H, so we need different letter. Let's write down as D. There is a D between C and C plus H, such that the integral is FD multiplied by the difference between C plus H and C, which is age multiplied by FD. Um, so we get that we have, therefore, can use different connectors from time to time. The integral here is just age FD. One big nice line. So the age and age cancel each other. And we get the limit of FD where age or when age tends to 0. First look, it looks a bit weird because the limit talks about age and the expression is f of d. Where is the age? Is a great man asked before me. But, huh?
Looks super confusing.
We are confusion. Where is the age? Pasta, pasta. You did this morning?
Can you go up a bit?
Yeah.
One how we got here because I'm a bit confused. So
Okay, so let's briefly walk through it again. We want to prove that the derivative of s is f. Suppose we look at some point, c. We want to prove that the derivative of s at c is fc. So we write down the definition of the derivative. We write down the definition of s, the integral between a and our point. Now, again, as our last proof, we have a difference between two integrals, which is one integral from the right points. And we can write down this integral as f at some point multiplied by the difference between the boundaries of the integral. We call it the intermediate value theorem, or the integral intermediate value theorem. Now, s plus age minus c is just age. So instead of our integral, we write down age and fd. The ages cancel each other, and we have the limit of fd. Now, we want to prove that the limit of fd is fc. And why is that? Now,
but there's no H anymore.
of course, so that's what I said. At first look, it looks a bit weird. But now, D is connected to H because D is between C and C plus H. Now, it's important to write down that the other way around can happen as well, meaning H doesn't have to be positive. But it's the same nonetheless, where age tends to 0, D, which is between C and C plus H, tends to C. By sandwich, D tends to C as well. I mean, we have write down in a different color, which shows blue this lesson. D is between C and C plus H. Ah, D is between C and C plus H. I don't want to write it down in black, like main text, because it can be, as we mentioned here, the other way around. It could be D between C plus H and C. And it doesn't matter because in both cases, it just goes to C. So when H tends to 0, D tends to C. And for our last, in Hebrew, say the last nail in the coffin. Yeah, I want to say sarcophagus, but it's coffin, right? Last nail in the coffin. if D goes to C, because F is continuous when when D goes to C, we have that FD, excuse me, goes to FC. Yeah. Yes, I agree. Because we talk about the limit, not about the point itself. Let's say we have C and C plus 1, so D is C plus half. And if you have C and C plus halves, D is C plus quarter, etc. So D tends to C. It doesn't really equal C, but it tends to C. And it's enough for continuity. When D tends to C, FD, the limit of FD is FC. It still be it's limit, yeah. I mean, if we have if you want to write down that way, D is between C and C plus H with a strong inequality. So writing down the result of the sandwich theorem is the limit of C, which is C, is between and sandwich the result of sandwich talks about weak inequality, equal or less. The limit of D and the limit of C plus H. And now the limit of C plus H is C. So we have, and the limit of C is C because C is a constant. It doesn't move. So we have the limit of D where D goes between C and C, which means the limit of D is C as well. So yeah, we start with a strong inequality, but sandwich itself states that the result is formed with a weak inequality. So that's our second theorem for today, the first part of the fundamental theorem of the calculus, or of calculus without theta. Any other questions? So now we can move on to the second part, which is the theorem about big F. It's called the Newton-Leibniz. No, it's Leibniz, so the is between for the I, whatever. Leibniz, it's a dead guy. Yeah. There's Newton-Leibniz theorem.
Oh, just to make sure, the last part we were just showing that we can integrate the segment because continuous or
we show that when f is continuous, this area function is an antiderivative. And now this theorem will connect it to the general notion of antiderivative of the big F, and we'll have our theorem of calculating, of a technical way to calculate different integrals without partitions or point choosings or oscillations or whatever. Just finding the antiderivative. We know from our first week here that it could be very hard to find the antiderivative using partial fractions and all this stuff. But we find it's better, of course, better than using partitions and point choosing, etc., etc. And we calculate the big F derivative, and we use it FB minus FA, and that's our definite integral. Newton and Leibniz, you know, were some of the biggest sharks of math. And when it comes to the calculus itself, Um, Historically, as far as we know, they both worked on the calculus at the same years and got to the same results um, independently. So it's one nice beef between the Leibniz fans and the Newton enjoyers who actually invented the calculus. But hmm? No, Newton was in Britain and Leibniz in some of the states that are now Germany. Um, as far as I know, they didn't know each other. No, we didn't have an email, so it was hard. Just like huh? They came up with it at the same time. It's not the only occasion it happened in the history of math. It's weird. It's a weird coincidence, but it's not the only one.
That's like they use the same things and what they're trying to solve different problems, but they do the rules, so they cannot break the rules.
First of all, it is true. I mean, at the same time, the British Empire and the Holy Roman Empire, which wasn't holy or no Roman or Empire, wanted to solve some problems about, I don't know, ships and traveling across the world and etc. So both Newton and Leibniz and other scientists were working on the same problems at the same time, not together. And I just wanted to say something similar. Carl Friedrich Gauss, is called the prince of math. And even as of today, when it comes to the mathematical domains, subjects that Gauss researched as well, one contemporary mathematician can publish some paper, do a research, just to find later that Gauss itself worked on it and already published. I mean, there's a lot of Gauss work still handwritten, not not on the internet. That's something amazing. He worked about a lot of things. So many mathematical publications and researches and work was actually already done by Gauss, but with the mathematician itself, not knowing that Gauss had already done it. So it's till today, with all our connection, email, and one phone call to everywhere we want in the world, that the same results are obtained from different mathematicians without them knowing each other. It still happened. As of today, you have to be at least if you want to publish it in English and not Chinese or Russian or whatever, you have to be the first one in order to get your paper published. But it did happen from Newton and Leibniz. So Newton-Leibniz theorem, let f be a continuous function and let big F be antiderivative of f. So let f be a continuous function and let f gadol be, let's say in some segment as we mentioned, be an antiderivative of f. We have, what is wrong with people? The integral from a to b is f at b minus f at a. I want to do a remark or a note or something like that. It works when f is just integrable and not necessarily continuous. as well. But as I mentioned before, our first part of the fundamental theorem, for what we are going to do and the exercise we need to solve, etc., we don't need the general case. And as our limited time allows me to do, not very long proofs, as I prove the first part of the theorem. When f is continuous, I continue to do it in the second theorem as well. So let's prove our second part of the theorem, not the remark. As we saw, S is an antiderivative of f. S our area function. But come, don't you run away. Moreover, I don't know. Yes, they look like the high schoolers, that finished the Bagrut exam. That's no. No, it's called the Bar Ilan program. I used to be a student at Bar Ilan program as well myself when I was young and without a beard. Um, you finish your math exams, Bagrut exams at I don't know. It's before you start high school, and through high school you're already working on your first or your BSc in math. Now they can have chemistry and computer science and even engineering. It's 4 years, but the IDF gives them another extra year before they're drafted. At my time, you can do math or math. And that's it. Moreover, we know that the difference between two antiderivatives of the same function, as we proved in our first lecture here, is a constant, that there is a constant C such that the difference between Sx and Fx is C. So now, by the definition, definition of S, we have that. On one hand, the integral is just SB. Because the definition of S is the integral from A to the point. So now the point is B. And on the other hand, the integral from A to A is, by the definition of S, SA. As we defined earlier in this lecture, the integral from A to A is just zero. Not A, it's zero. And we can write that the integral of f from A to B is the integral, I call it, as I mentioned before, I don't know, trick shafel, shtick, nefarious, so the real word is. From A to B minus 0, and this is SB minus SA. Now S is F minus C, or F plus C, whatever, doesn't actually matter. The C cancels itself, and we are left with FB minus FA. So just by the definitions of S and integral from point to itself, it's the second part of the theorem, but it's actually a corollary from the first part of the theorem. Yeah. Um, the difference between and a big F and S is a constant C. Why? That's a proposition we saw in our first lecture because on one hand, is an antiderivative of the function f, as we proved in the first part of the theorem, and f is an antiderivative of f on the other hand because this is what we're given here. The theorem says that when we already have a big f as an antiderivative, which is given to you, you can write down the definite integral as difference between fb and fa. So we have s antiderivative because of our theorem and f, etc., etc. Yeah. Any other questions? So, I want to do two things before we finish our lecture. I think we have the time for it. The second one is talk about, as far as I understood, something that was already mentioned in your homework, the difference between antiderivative and the definite integral. Yes, we have our second part of the theorem, which is nice, FB minus FA. There's still difference we need to discuss. But the first thing I want to do is just have a simple example. So now, when we need to calculate a definite integral, we will do it using the antiderivative as long as an antiderivative exists. Instead of FB minus FA, one can write I write down as something like that. Fx and x is a and x is b. Oh, no. B and x is b or something like that. Yeah.
Sorry, I'm rereading the last one. Why do you need to say that the integral for a certain point is zero for the to work?
Because I want to have FB minus FA. Where does the FA come from?
Oh.
From the SA. Why? How can I write down minus SA in the first place? Because it's zero. You can always write down minus zero if you want.
Yeah. No, and like, and SB comes from the integral from A to B.
Yes.
And we can prove that we can write like this. Yeah, that's like
the definition of S. Definition of S is the integral from A to the point of S. Now it's B, so it's the integral from A to B. And that's why SA is zero because the integral from A to A. Let's have a simple example. For example, let's say we want to calculate the integral between 1 and a number you like. 67 of x. So one antiderivative of x is enough. We know one, it's x squared above 2. Yeah. As I told you before, when I grow older, names become more and more just, I don't know what the word looks
I
like.
watched a video explaining it because I'm too old to, and it does never happen.
I'm not a conspirator uh, enthusiast as well, but it looks like someone on purpose trying to dumbing down younger generations, make them stupid. Woo! I mean, I'm not very old. I can use memes myself, not just the simple templates, but it doesn't make any sense. The 6-7 stuff and all the
That's not supposed to make it dumb. It's just like dumb stuff. It's not supposed to make sense.
my
Of course, it
brother
has to make some sense.
my brother told me yesterday, it was maybe Friday. I mean, oh, you don't believe it. I'm listening now. No, I'm listening in loops again and again to this song. It's a choir. It's amazing. And I was like, what is it? And it's like the tung 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 sahur. You know the meme? Tung 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 sahur with the. Oh, you see, you're you're better than me. Um, there is all this brain rots last year of the Bombardilo Crocodilo and but yes, yes. So one is tutu, so I think it's Indonesian, not whatever. So it's just someone actually edited it and put effort and time to edit this stuff into some choir song. It is fire, I have to admit. It is fire, but it's so dumb. It's like tuk tuk tuk, so it's a ballerina, 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 crocodilo. And it's dumbing down. I think. So we have 67, you choose it squared above 2, and it's a number. Very nice. Now, when we were at high school, that's how we calculated integrals. Well, when I was in high school. But we are smarter than this. We know that that's how we started our first lecture. We know that, first of all, antiderivative not always exists. I mean, we have, as we mentioned in the first lecture, if a function has like a jumping point of incontinuity or whole point, removable incontinuity, so it does not have an antiderivative. And moreover, functions that do have an antiderivative, like e to the power of x squared, and I write down immediately, do not have an elementary antiderivative. So we cannot find it. We cannot find f, big F, even it does exist. I mean, now one can write now, the antiderivative of e to the power of x squared is the integral from a to x, and but you cannot use it to actually calculate the integral. So that's, as I mentioned, the second and last thing I want to talk about today. Our Let's write it down as antiderivative versus the definite integral. When I was younger, there was a YouTube channel called ERB, Epic Rap Battles of History. You know it? Yes. So we can ask them in the comments to make a video of antiderivative versus definite integral. On one hand, there are integrable function which the whom's don't have an antiderivative. For example, a function with an incontinuity. So right now, incontinuity point such as, let's write down f(x) is let's say 0 when x is between 0.5 and 1 when x is between 0.5 and 1. So as we said in our first lecture, is integrable. In our last lecture, we saw that is bounded with a finite number of incontinuities. We yes, there's a little space between them. It's integrable as we saw it on lecture 5. Ladies and gentlemen, it's lecture number 5. And on the other hand, but it does not have an antiderivative, as we saw on lecture 1. A function with jump in continuity, where the one-sided limits are different, does not have an antiderivative. So, in order to calculate the integral of such function, we can, for example, look at the function parts, meaning, first of all, we calculate the area between 0 and half, and then the area between 0, half and 1. And as we mentioned, the integral from a to b is integral from a to c and c to b. So we can divide it to different domains, each of which we can find that derivative. I asked Nir to do such example, at least one, in the practice. Something more interesting with, I don't know, every point is whatever. You don't want to spoil it for you. And second thing we can do is not very nice or convenient, but we don't have another choice. We can use the definition. We know that f is integrable, so we can choose whatever sequence of partitions we want and whatever sequence of point choosing we want, but we need to choose such sequence of partitions and sequence of point choosing and calculate the limit of the Riemann sum. And this will be the integral of the function. We don't need to prove that it's integral. We don't need to look at every sequence. We know it's already that it is integrable because it's bounded with finite number of incontinuities, as we mentioned on our last lecture. And in order to calculate, we need to choose, yet again, some sequence of partitions, some sequence of point choosing, and calculate the limit of the Riemann sum. And as I said, I asked Neil to do at least one example of this kind in the practice. I want to add something, and moreover, or furthermore, whatever. We mentioned that as well in our first lecture. There are functions for example, e to the power of the x to the power of 2. That, no. That do not have an elementary antiderivative. Function Sx, which is the integral from, wait, how did that happen? From a to x of e to the power of 2 to the power of 2 dt is an antiderivative of e to the power of x to the power of 2, as we proved on our first part of the fundamental theorem. But we cannot technically use it to calculate the integral. I mean, I can't put it, I mean, I can, but it won't go anywhere. Not that, we know in this example, x becomes x squared above 2, and we can plug in 67 and 0 and have our explicit result. Write it down, but it does not help. So we have, on one hand, functions that do not have an antiderivative, be it a function without an antiderivative or a function with an antiderivative, just not an elementary one. It's all the same when it comes to the fact that we are not able to use our second part of the theorem to calculate the area, to calculate the integral. And on the other hand, there are functions that are not integrable because they are not bounded, and the definition of integrable is yet again two conditions. The second one is all the Riemann sums go to the same limit, but the first one is the function to be bounded. And if a function is not bounded, it is not integrable. On our next lecture, I think we can start the subject of integrals of unbounded functions, but everything in its time, as you say in Hebrew. The functions are not integrable, but do have an antiderivative. Because our Darboux was the name of the dead French guy from our first lecture. The Darboux theorem that we mentioned in our first lecture stated that if a function has an incontinuity of a hole or jump point, it does not have an antiderivative. But an incontinuity of tending to 0 or something like that is okay. Function can have an antiderivative and still not be bounded. And for example, want it to be a little creative, let's have a look at the following function. Yeah, something like that. You watched my videos, you read my notes, you asked GPT, or you get it with yourself, which is impressive.
I got homework
Mm-hmm.
and I'm like trying to figure out what the correct was for me. And I looked it up and this was one of the answers.
Yes, as we mentioned before, maybe you should ask Nir to be sure. You should wait to the last practice before the date of the date of submission of the homework. Maybe Nir is planning on you knowing to know the material of the last practice in order to be able to solve all the exercises, all the questions.
I have other things to do.
Of course, you as well. You can ask him, for give us some more couple days or something. I don't think it'll be cruel. So something like that. Look, that's the big F. That's the antiderivative. We can prove that we can derive it and have our little f. By definition, f at 0, which is the derivative of f, big F at 0, is the limit where h goes to 0 of f at x minus f at 0. No, f at plus h. 0 plus h. Above h, well, f0 is just 0, and 0 plus h is just h. Minus 0, we don't have to write down, and f of h is h squared multiplied by sinus of 1 above h squared, which is a very nice function, but it is bounded. So when the h squared and h cancel each other, and we are left with only age, the limit is 0 because the douchebag it was written because sinus of 1 above edge squared is bounded, multiplied by something that tends to 0, it goes to 0 as well. At every other point, we can derive f with our rules. It's a multiplication of function, which is not very nice, but we can handle it. It's 2x multiplied by sinus and x squared multiplied by the derivative of the sinus, which is cosinus. And the inner derivative, as we say in Hebrew, derivative of 1 above x squared, which is minus 2 above x to the power 3. And our little x and x cancel each other. And we're left with x in the denominator. We have 2x sinus minus 2 above x, the cosinus. To write it down, in conclusion, this is in little f. If we have the function little f as this abomination when x is not 0 and 0 when x is 0, and we have the antiderivative, which is that, we see that f has an antiderivative. It's the big F where we started. The derivative of f gadol, big F, is small f. But on the other hand, yeah, no, I'm just sitting here now, enjoying our integrals. F has an antiderivative, but it is not bounded because of the x in the denominator. It tends to infinity, it goes crazy. So it is not integrable. So there is a strong connection between antiderivatives and the definite integral. It's the second part of the fundamental theorem, but they are not equivalent, they are not the same. A function can be integrable, and moreover, we can actually calculate the integral without using an antiderivative, without the function itself having such an antiderivative. And on the other hand, a function can have an antiderivative without being integrable because it's not bounded. So that's what I want to say here. As I understand, it is connected to some of the questions in the homework. Okay, our time has come. Any questions? Yeah. No, because when x tends to 0, the 2 above x tends to infinity or minus infinity, wherever you come from, and the cosinus is not helping. It's not helping it just go to 0 like this. So it's not bounded. Any other questions? Okay, so we can finish. Hope you all enjoyed our time.